is entitled Chain Growth for the Hydrogen CO Reaction over Nickel Aluminum. It is authored by D.M. Stockwell and C.O. Bennett of the University of Connecticut. Professor Bennett will be presenting this paper.
This work is based on the PhD thesis of David Stockwell, who was just finishing his work at the University of Connecticut. It concerns chain growth on nickel, which of course is a very good hydrogen catalyst, but we can get up to C5 and C6, and we are just developing this method of experimentation so that we thought it would be good to choose a system where the chain growth, the chains were not too long. This is the catalyst we're using. It's made by impregnation, and there's nothing unusual about the catalyst. All we wanted to do, as I said, is to try to study the chain growth. And of course, in order to do that, we have to be sure we understand the initiation processes, the formation of the surface monomer, so to speak, in order to consider that rationally. We used a small volume reactor which behaves superficially as a stirred tank, at least, and we are doing most of the experiments by steady state tracing. What that means is that we have a feed of CO and hydrogen, and we run everything at constant temperature and pressure, atmospheric pressure, temperatures being the order of 220 to 270 degrees Celsius. And we switch from CO, ordinary CO is the carbon-12 in it, to carbon-13 containing CO, and in that way we do not disturb the chemical steady state of the reaction, and we can then observe the ingrowth of the carbon-13 into the various products and make some deductions about the sequence of steps and the way in which the chain growth is occurring. So we'll start to look at some of those experiments. Quantity Z here is the fraction of carbon-13 which occurs in the molecules of a given product. For instance, in the CO there, the Z would be the fraction of the CO molecules in the gas phase, which are carbon-13 CO molecules. And this represents a sort of blank of the whole experiment. The F here stands for the forcing function. That was obtained by argon, but we can view it as if it were obtained by CO. In other words, if we make this switch and we bypass the reactor, and so of course there's no absorption or no reaction, then the CO would respond according to that forcing function. That's supposed to be a step function, but of course it's not a step function because of the operation of the valves to do the switching, and because of the response of the mass spectrometer, which was used to follow various components. And then if we do the next step in the blank experiment, then we would use argon again, but it's as if we put the CO through the packed bed reactor, which is a very, very shallow packed bed, so it behaves, as I said, approximately as a stirred tank, mixed flow reactor. And if we do that, then the M curve would be what would happen if no CO adsorbed on the surface of the catalyst. In other words, just a physical mixing in the gas phase, which would cause the CO to come out more slowly than the forcing function, which is supposed to approximate the step function. And finally, the third curve here is what one actually sees, and supposedly some analysis will show that the difference between these two curves represents the CO on the surface during the steady state experiment, which is, of course, at reactive conditions. And of course, the difference over here between these two curves is proportional to the amount of CO which is held up in the gas phase. Well, we have to be rather careful about this in order to get a good measure of the quantity of CO which is absorbed. And we have simulated these various curves by a series of stirred tanks and viewed these things on the computer, and we get good fits when we assume that the little reactor behaves as a mixed flow reactor. Well, we have to say a little bit more now about the behavior of the CO. Basically, it's known that CO exchanges very fast on the surface, but I think just to review this, I'll show you this one little diagram here. The CO is fed in at a certain rate here. This box or pool represents the CO in the gas phase. Most of it doesn't react. We have about a 3 or 5% conversion, and the rest of it has to react, but it has to go through the surface CO. And there are two extremes, of course. We could have no exchange, that is, the CO really is completely irreversibly absorbed on the surface, then the R minus would be 0, or we can have very fast exchange so that R plus and R minus here are large numbers compared to R forward, so that in that case the CO on the surface follows its composition, its isotopic composition, then will stay in step with the isotopic composition of the CO in the gas phase. Actually, that's what we want, as we'll see in analyzing how this all works. See that it helps us in our analysis if we can assume that the surface CO has the same carbon-13 fraction as the gas phase CO. Because, of course, we measure the gas phase CO as it comes out here, and that's the curve that I just showed you. There are two parameters which govern how this process works: the amount of CO on the surface and the exchange rate here, so to speak, and this quantity beta, the ratio of the backwards to the total flow reaction rates. Of course, the reaction rate itself is constant all the time. The exchange rates are superposed on the steady state. Well, we can model this with writing down the balances, the differential equations, and so forth. And we do find that we can vary the parameters, the quantity of CO on the surface and the beta. And when we do this, we found out that beta is a very large number, the order of 100. So our assumption is good. I could have just said that it was, but I thought it would rather be interesting to realize that even if we had a situation where beta were not very large, we could simulate that process supposedly. Well, now let's go down to the interesting part, is what happens to the other things. We'll go one at a time. Here's the methane. Again, this is pretty well known that the methane comes out more slowly. The CO comes out very fast. And this, as I say, represents you might say, the surface composition as far as the fraction of Z, the fraction of C13 in the CO goes. That's what Z still means this. And of course, now Z means for the CH4, the fraction of C13, which is the methane which comes out. And this happens slowly. And supposedly this is because the CO after dissociation forms forms carbon, which is, and the rate determining active center then is some version of that carbon. In other words, we will refer to this as usually done by calling it CHX, and the X can be 0, 1, 2, or 3. Of course, it can be more complicated than that, but for the present purposes, it's sufficient species is one of those CHX species. Well, then, by doing the same sort of analysis, we can determine the amount of carbon on the surface, amount of CHX on the surface, and of course, that means that we'll find out there's quite a bit, there's a certain quantity, and also there's a certain reaction rate constant which goes with that quantity. So the idea that we're going to work on now is that we have now the polymerization on the surface, and that the monomer supposedly is the carbon which has produced this CH4. In other words, that this CH4 curve here, this Z for CH4, represents the rate at which the carbon-13 is appearing in the form of CHX on the surface. And that supposedly is going to add to the growing chains. However, this is the most accepted view for quite a few Fischer-Tropsch catalysts. However, I'm going to do things a little bit backwards. I'm going to show you another case because it does correspond more to what we find in our experiments. It's also possible that CO could insert in the chain growth instead of CHX. And if that were the case, then the monomer would have to have the CHX to start making methane, and then the CO on the surface would add at this rate, then as the C13 will appear at that rate in the added monomers, and influence the rate at which the carbon-13 would appear in the higher hydrocarbons which result. I'll just draw a sketch of what I'm talking about. Here's our surface CO, and makes CHX, and this is hydrogenated. Supposedly, there are two genetically significant steps here: the dissociation and partial hydrogenation to make this surface intermediate, and then the hydrogenation of that to make methane, so that there are finite quantities. We've measured these. The surface is about 2/3 covered with CO and 1/4 or so covered with CHX fragments. Well, then according to the Anderson-Schultz-Flory procedure, you presume that the growing chains are attached at one point, and the CHX inserts in each place here. And you see that what happens now with the carbon-13, if this is the scheme, is that the carbon-13 goes through here and grows in at a rate which is dependent on the rate at which the CHX contains carbon, or which the carbon-13 appears in the CHX. Well, in order to simulate this or to analyze results, one has to know the size of these boxes here. Most of the evidence that one can find for nickel chain growth would indicate that the quantity of chain fragments which are held on the surface is very small, unlike what we heard earlier about ruthenium, where there seem to be bigger quantities of these growing chains held on the metal surface. So the one logical assumption is that the size of all those pools for the higher hydrocarbon fragments is very small, so that in that case you can see that all the other compounds, CH4, C2, the C3, C4, all those compounds would have C13 appearing in them at the same rate as methane has appearing. Now I've lumped together all the olefins and the parabens in each one of these boxes here, and we'll have to figure out how to do an experiment to agree with this scheme. All we want to do in order to test out this scheme is to measure the fraction of carbon-13, which is in each carbon number. We don't have to know a detailed analysis, divided up into olefins and branch chains and so forth for each carbon number. So that's how it would, the carbon-13 appearance would look for the CHX insertion. One is the forcing function, two is the CO, carbon-13 of the CO, that's the CO monomer, so to speak. And 3 and 4 then would represent what happens in the limit of a small time constant, that is a small quantities of the higher chain fragments on the surface during the polymerization. In other words, the Z would go up at the same rate for methane and all the higher hydrocarbons. And then you see it's quite simple to see that if the CO insertion, we have a different situation. Here we initiate the chain with the CHX as usual, then we add to it, you might see the monomer now becomes a CO on the surface, and we add CO here and here. Well, remember that the CO carbon-13 content is going up very fast, and the CHX carbon content is going up slowly, so that when we now add these other COs here, the carbon content of the higher hydrocarbons is going to go up faster than the carbon content of the lower hydrocarbons. And in the limit, of course, the response for a very long chain, which is practically all made up of the CO, not from the CHX, that would go up at the same rate as the CO, as the 13C content in the CO. And we can simulate this again for the same limiting case of very little storage on the surface. And we get curves like this. This would be the methane curve, the ethane and propane and so forth curves would go up in that way. Now I might just mention that either in this case or the previous case, maybe the previous case is easier to look at. If we of course can easily do calculations where we would say that we don't have this limit here. We can say there are constant quantities of the various, certain quantities of the various chain fragments on the surface, and that would always make the response curve come below this methane curve here. I think you can see that that's reducible too. If we have delays by storing up the carbon-13 as it goes through the chains there, then these delays should result in the higher hydrocarbons appearing less rapidly than the methane. Now let's see how we can do an experiment in order to see what really happens. This experiment is similar to one we saw this morning. We're doing it in a slightly different way. We have a multiple sample valve, and we do our switch from carbon-12 CO hydrogen to carbon-13 CO hydrogen, and then we have 16 loops, and we turn the valve every few seconds and trap a sample, and then analyze afterwards. And we send each, and afterwards the whole experiment, the whole transient experiment is done. We send these in a hydrogen carrier gas. We send these stored up samples to a GC column to separate them into the olefins and paraffins, the various chain numbers. And then we, instead of oxidizing them, we use hydrogenolysis, does the equivalent thing, convert them all to methane, and then we can send the methane to the flame ionization detector or the mass spectrometer, and the flame ionization detector will tell us the total amount of each hydrocarbon, according to the peaks we get in the mass spectrometer. And the mass spectrometer we can set to mass 17. We have high resolution, so we can avoid problems with water, and we can get the fraction of each mass number then, which each carbon number, which is carbon-13. So we can do an experiment which corresponds to the analysis I mentioned to you before. The only thing that remains is to show you what we get. This is one of the experiments we get here. We have one of the results we get. And here, Z sub n refers to each one of the carbon numbers. I've reproduced here the continuous curve for the methane. And each time we turn the valve, we make a little bump in these curves here. You see it's not a very large disturbance. And that sort of confirms good working of the valve and the timing and so forth. And then we have the various hydrocarbons here. And you see, much to our surprise, that all the points don't lie on the line or below the line, they lie above the line. That is, as we go, for instance, here, we have methane and ethane, and propane and butane. That is C4, there's some ethylene in there. And these are the steady state quantities here, and these are the conditions over here, temperature, conversion, and so forth. Of course, this is a very poor Fischer-Tropsch catalyst, giving us an alpha of 0.26. Well, now, this certainly confirms the fact that the notion that there's very little carbon-13 which can be stored up anywhere on the surface in the form of partially glowing chains, or nickel at least, because all the curves are close to this line, and certainly they lie above it. And of course, the precision is not incredibly good, but it's quite good. You see that in practically all cases, the experimental points are in the right order. Of course, if we go far enough over here, they all should come on to a common value at once. We've done quite a few runs like this. I'll just show you one more. This one is at a lower temperature, where we have much larger numbers here, and we can go up to C6 in this case, and you see the quantities that there's definitely a tendency for the higher hydrocarbons to come out before the methane and the ethane. The ethane seems to come out very close to the same time as the methane comes out. So that how to explain this then? Well, of course, I refer to what I've already said before. However, we did try to figure out whether there was any other way that the carbon-13 could come out ahead of the methane response there. And it really is difficult to imagine. Presuming that the carbon-13 has to go through the CH on the surface for to make methane, then if it's going to come out faster than the methane, it had to go short-circuit that step somehow. And the only way we can see is some kind of CO insertion. It might be CO with something else attached to it, but at least it has to be some entity which has a response time which is like the CO response, that is much faster than the methane response. Actually, we can say that there's a mixture of the two processes occurring and simulate this. This is just to put in a picture what you can say in words. We can fit the data by assuming there's a monomer which is effectively half made up by CHX insertion, half made up by CO insertion for everything but C1 and C2. And then we get curves like this, which approximately fit the data. Well, this little experiment here really is more aimed at trying to understand the mechanism of chain growth than it is in making a quantitative simulation. It's just to test your ideas by making a mathematical model like this to make sure that you didn't overlook anything. So I might just mention one or two other things. It's not unheard of to propose that CO insertion is important. This has been found by Kelly and Szymanczyk which he experienced, and opponents had proposed this in the past. So that the conclusions that we can reach are very brief. One is this Tn goes to zero. That's another way of saying there's very little accumulation of growing chains, and also that it doesn't appear that the higher hydrocarbons are produced by either pure CO insertion or CHX insertion. Thank you very much.
Questions? Yes, please come up to the mic and identify yourself.
Brian Camiso, UC Berkeley. From your flow rate and the amount of catalyst you have, you can calculate the dilution time, which is the amount of time it takes to replace all the 13CO, all the 12CO with 13CO. And for your sample, that seems to be between 8 and 40 seconds to replace the service CO with labeled CO.
No, that was 2 or 3 seconds. Maybe we better turn it on again. Which one is it? Very good. That's the very first graph I showed. That's no, it's all over by 6 seconds. The time constant is only a second or a second and a half.
Right. Stockwell kindly enough gave our group a topic paper. Told us that he's only able to monitor one mass at a time. So I'm curious if these were taken at the same time.
Well, that's what the multiple loop sampling valve is for. That is, we trapped a sample at a given time and then did the analysis by gas chromatography and mass spectrometer afterwards.
Okay. He also mentioned the resolution that was 2 seconds for the GCMS analysis. And for the mass spec, he's going to use to monitor the course of motion.
I mean, the resolution in time for any atmospheric pressure isn't very fast. I mean, this curve here represents, you might say, the time resolution, which is 2 seconds. Yes. In other words, if you put in the step function to bypass the reactor, you get that result, which comes both from the gas dynamic part of it and from the electronics and whatever else is going on in the mass spectrometer.
Any other questions? Yes.
Your results present an interesting situation because it returns us to the possibility of CO insertion as a chain growth mechanism. I'm wondering if there aren't other explanations that might give the same transient response. Let's say that we had 2 pools of carbon, one which reacted slowly, one which reacted rapidly. And the one that reacts slowly, in other words, the holdup is longer there, produces selectively methane and ethane. Now, I think I'm right in my reasoning that I would get an inversion if I assumed a chain growth by CH2 addition or CHX addition. Under the circumstances I've described, I'd get an inversion where the methane and ethane would be delayed relative to everything else because there's also production through the slow pool. And this would give you this kind of band separation that you showed on your next to last transparency, because it looked like there was a grouping of C3 to C6 in one set, and C1 and C2 is the lower set. Now, I'm asking myself, how might I suggest an experiment that would test this hypothesis? It would seem that if you do the transients after different times on stream, so that you could build up different populations of these 2 pools, you might be able to sort this out. Did you do this kind of experiment?
No, we haven't done it. We've done this with iron, and we do see differences. However, I'm not sure that I understand just how this would work the way you propose it, Alex, because the C3 supposedly has to come from the C1 and C2, doesn't it?
If I have 2 sets, I have 2 sets of carbon, one which will make C1 to Cn, and one that only makes C1 to C2.
Okay.
That's my postulate.
I don't mind one set that makes only C1 to Cn, but you think there's another set, another group of carbons, or say another carbon pool, which starts making C3 and up.
No, makes only C1 to C2, doesn't make C3 and up.
Well, yeah, but where does the C3 and C4 come from?
C3 and C4 are coming from the first pool of carbon.
But then how can they come out faster than the first pool of carbon?
What slows things down, see, you're looking at the percentage tagging. What slows things down is that the second pool of carbon delays the approach to unity on your Z axis, so that you would expect to see a falling down or delay in the full tagging of your C1s and C2s.
Yeah, the other curve, the CH4 curve, of course, actually does not represent the response to a single pool. It agrees with what you had in your recent article, of course, with the Montes and so forth. And that is that you can, it does seem that there's some non-uniformity in the reactivity of the carbon. But that CH4 nevertheless represents the result.
It's the total.
The total.
Yeah. But its time constant depends on the fact that it comes from two pools.
Excuse me, this is a very interesting discussion. We're beginning
I
to
don't want to
run
dominate it.
So, thank you very much again, and we have to move on to our next speaker.